All right, so we're going to describe the connection between population distributions and populations. So this is too technical. Statisticians are interested in studying samples drawn from populations. Random variables are important because when an item is drawn from the population, the value observed is the value of the random variable. The probability distribution of a random variable tells us how frequently we can expect each of the possible values of the random variable to turn up in a sample. So a parking facility contains 100 parking spaces categorized as follows. So we have the cost, the type and the cost. A parking space is selected at random. We're going to let X represent the hourly parking fee for the random space, and we want to find the probability distribution of X. So where this breaks it down a whole lot, and we're just trying to make that probability distribution, all we really need to make that distribution is we need to decide what X is going to be really be, and X has to be something that is numerical. And what we're told here is that we're going to let X be the hourly parking fee. So remember that when we're dealing with we're dealing with our variables, we always order our variable from smallest to largest. So what I have here is that my variables are either I'm going to pay the 150 fee, which we know covers uncovered long-term parking. I'm going to pay the $2 fee, which covers covered long-term parking. I can pay the $4 fee, which is uncovered short-term parking. Or I could pay the $4.50 fee, which is uncovered short-term parking or covered short-term parking. It seems funny that short-term parking costs more. Next, we need to figure out the probabilities of each event. So we have 1,000 parking spaces. So that means the probability of the probability that you would end up in the $1.50 parking. Sorry, my stuff has got too close to each other. Is 0.423. The probability of being in the uncovered long-term parking or paying the $2 parking fee, that will be 0.124. The probability of paying $4 with the uncovered short-term parking, like if you randomly had to pick a parking spot, that'd be 0.057. And the probability, no, this is going to add up. I thought it was going to add up first, not add up for a second, that I pay $4.50 or uncovered short-term parking is 0.378. So this is my population. So it tells me about my population. So this particular parking facility, I know that 42.3% of my parking available is going to be that $1.50 parking. I see that my $4 parking is the least common because we have more, it looks like uncovered long-term parking. Sorry, I was just reading this here. That's going to be my uncovered short-term parking. So I have less parking for that available. All right, so this is another population that we're organizing. So this is a population of 5,000 undergraduates are registered at a certain college. Of them, 478 are taking one course, 45 are taking two courses, 568 are taking three courses, 1,864 are taking four courses, 1,357 are taking five courses, and 88 are taking six courses. X is going to be the number of courses taken by a student. So if we want to make our probability distribution for a population, so our big X. So just to make a point here, big X we're using to represent sample variables. And big X is our population variable. Okay, and then this is going to be P of X. So how many people are taking one course? Well, we have 5,000 students, and we have 478 out of the 5,000. So that is going to, whoa, there we go, 0.9, 0956. So 9.5% of my students are taking one course. How many are taking two courses? Well, that is going to be the 645. So that's going to represent 0.129. So about 13% of them are taking two courses. Three courses, that is going to be 568 students. So that is that 5,000, that is going to be a little over 11% of them. Four courses. This is where it starts to kind of amp up a little bit. Oops. There we go. That's 1,864. So that is represents about 37% of my students. Five courses. So we have 1,357 are taking them. That is going to be about 27% of all my students. And then I have just 88 out of the 5,000 are taking six courses, which is almost 2% of them. So that would be my probability distribution. Okay, and the last little bit here, so this is going to lead us into something that's, I believe is chapter 8. I guess we'll see when we get there. I can't remember if it's 7 or 8, but we're talking about a mean being a random variable. So this is a sample mean. So sample means are actually random variables as well. So often when we draw a sample, we compute a sample mean, which is going to be our X bar. The quantity X bar is a random variable because its value is different for each sample. So a probability distribution of X bar is usually difficult to compute. We're going to go through a little bit how we do that. It's not that complicated as much as they make it sound. We will learn a way to approximate the probability distribution of the sample mean when the sample size is larger, or the sample size is large in a later chapter. So by large, we're meaning it has to be like 30 or more. But that's something that we're going to get into later. So just remember, not only are variables themselves random variables, but every time I collect a sample and I collect a mean from that sample, that is also a random variable. Also, every time I collect a proportion, or I collect a median, or I collect a standard deviation from a sample, those are all random variables.